这个不知道是谁的。
I'm ready.
Okay, so you can just go ahead to be yours.
So honorable judges and distinguished competitors, this is Team PKP and Body Report, number 14 ruler trick. So here's the problem statement. First, place a ruler on the edge of the table and throw a ball at its free end. The ruler will fall. However, if you cover a part of the ruler with a piece of paper and repeat the throw, then the ruler will remain on the table, while the ball will bounce off it. Explain this phenomenon and investigate the relevant parameters. So our main focus will be on finding the threshold value that can hit off the ruler to the ground, and how does the atmosphere pressure affect the torque. And here's the outline. First, we do the observation, theory, experiment design, result, conclusion, and future experience. So here's the observation in the video. You can see that when we put the ball down, the ball will bounce off the ruler. And so here's few variables to consider. First is the bending angle of the ruler, and secondly, the air gap between the paper and the table, and third, the rebound height of the ball. And for the observation, you can see that because we think that the air pressure will given is the main factor that make the ruler remain on the table. So we do another version that we create an air gap. So from the video, we can see that when there's an air gap, the ruler will fall off the table. So we can make sure that this is, we can make sure that this air pressure has given the force to let the ruler remain on the table. And the theory is the lever roll. So in this situation, when the counterclockwise torque is bigger than the clockwise torque, the ruler will fall off the table. But if the clockwise torque is bigger than the counterclockwise torque, the ruler will remain on the table. So in this situation, it's like this. So here's three theories. First is the impulse momentum theory, and the secondly is the torque. And the third is the integrating theories that we can prove that it's the air pressure that keep the rulers on the table. So here's our experimental design. So we use the bracket in the water pipe. And we use water pipe because we can make sure that the trajectory of the ball will remain straight, and the ruler and the paper. draw a line every 2 centimeters on the ruler because we want to measure the critical value of the hit point, like the critical length of the ruler that will fall off the table. And the paper we use is the poster paper with length with 42 centimeters and width is 10, 15, 20, 25, 30 centimeters respectively. So in the first experiment, we changed the width of the paper. So we changed the width of the poster paper with 5 volumes, a value, and we want to find out the critical mass of the ball. In the second experiment, we changed the force arm. Just like the picture we have shown, so we draw the line on the ruler every 2 centimeters. And our experiment is like this. We use tracker to measure the movement of the motion and draw the VT graph of the object. And we found out the change of the velocity and the contact time. So in our prediction, we predict that the harder ruler will have a greater critical mass, and the critical mass increases when the width increases. Third, the critical mass will increase when the force arm decreases. And then fourth, the critical mass will decrease when the height increases. So this is our prediction. So for the result, we can see that when the ball fall off to the ruler, the harder ruler will remain straight, so the air pressure will come in. But the softer ruler will have a deviation, so the air pressure will come in. And so we have found out that the harder ruler can have a bigger critical mass. And this is our data analysis. This is the relation between width and critical mass, relation between width and critical torque, relation between width and pressure loss torque, and relation between force arm and critical mass, relation between force arm and critical torque, and relation between force arm and critical torque, and relation between force arm and pressure loss torque, relation between height and critical mass, relation between width and critical torque, relation between width and pressure loss torque. So in our conclusion, we found out that the harder the ruler is, the bigger force needs to be hit off the ruler. And when the ruler is lifted, the air will go underneath the paper and make the air pressure more balanced and lower the torque caused by the pressure. And the more width the paper is, the heavier the ruler can suffer the weight. But there will be a limit. And the shorter the force arm is, the bigger force we need to hit off the ruler. And for future experience, we want to find out how the pressure actually changes at different points, because in our experiment now, we cannot really measure the air pressure in every single point. But we want to measure, but in our future experience, if we can measure the different point of the air pressure, we think that there will be a more accurate result. And we want to find a function of the air pressure. Since we cannot measure every point of the air pressure, we don't really know how the air pressure influences the whole system. But if we can find out the difference in every point of the system, we can find out the more accurate function of the pressure. And also, we want to find out what the critical mass is to influence the whole system, including the variables we have mentioned above. And here is my report. Thank you.
Okay, so here is the opponent. I want to first ask the reporter, how do you define the term bending angle, as you mentioned in your presentation? How do you define bending angle of the ruler?
So at the beginning of my experiment, we have found that the ruler will have a little bit of deviation. So we want to measure the bending angle, but in the end we didn't measure it because we think that it's the slight factor.
So I think the bending of the ruler is a minor factor to be considered.
Do we think it's minor or?
So you think bending angle is a minor factor? Okay, thank you. Next question. How do you define the ruler is hard or soft?
It's competitive. So we get two ruler
and compare the stiffness?
Yeah.
Okay, thank you. And how do you define the volume of the air under the paper?
So we didn't measure the volume of the air under the paper, but we watched the deviation of the paper.
How do you define deviation of the paper?
Like how much it changed in the phenomenon.
So you mean you measure how much the ruler lifts the paper?
Yeah.
Okay, thank you. And in your theory of the torques, do you assume that the ruler is a rigid body?
For the hard ruler, we believe it's a rigid body, but for the soft ruler, we don't believe it is a rigid body.
Okay, thank you.
Opponent, please. Sorry, question.
So this is the opponent from Team Miracle, and we're opposing the problem ruler trick. So as a brief recap of the problem states that you would place a ruler on the edge of a table and cover it with a paper. Then apply torque using a ball on the outer side of the table. Then the ruler won't fall. And we need to investigate and explain this phenomenon. So in the problem, we need to focus on so firstly, we need to define the falling of the ruler, and nextly, we need to and then we need to explain the falling mechanism of the ruler. And the next thing we need to consider whether the ruler will fall, the boundary conditions for the ruler to fall. And the next thing we need to study the boundary condition depend on relevant parameters. Okay, so for general pros and cons for the reporters, we think that you have well-organized report and a quantified theory in the torque, and you compare your theory with the experiment, but we think that you have fuzzy terminology in terms of the bending angle and the stiffness of the ruler, and we think that you lack comparison of different measuring methods. So for the report overview, we think that for the preliminary experiment, you observe the ball bounce off the ruler when covered by paper, and we think that you get the key feature and you have a clear observation of the phenomenon. But we think that you didn't actually define the falling of the ruler and the bending angle of the ruler, or the air volume between the paper and the table. But you did change the air gap between the paper and the table. So that's a good change in your setup. Okay. And as for the modeling, you considered the torque balancing, but we're not sure about whether your theory is applicable to materials that is elastic, and you modified it for variable force using an integral for the impulse, but you didn't mention the limit of the theory. That's a concern. Okay, as for the experiments and analysis, we remember that you did parameters such as falling position, the width of the paper, and the elasticity of the ruler. But we don't think you defined the elasticity of the ruler very clearly, and you analyzed it with tracker, and you have done VT graphs of the falling process. You compared your experiments with your theory and concluded that with the ruler getting harder, the bigger the force needed to get it off the table. So we think that you have missed some key parameters, like whether the ball's momentum will change the phenomenon, or if the paper's elasticity changes the phenomenon, or if the ruler changes position, whether it will change the boundary conditions of the ruler will fall. So nextly, the points we want to discuss with you is about one of them is about the modeling. We think that you didn't incorporate air pressure into consideration of your model, and we don't think you have considered elasticity of the ruler in your torque balancing model. And for experiments and setup, we think that using a pipe, you didn't control the rotation of the ball very clearly, and then adding an angular momentum to the ball. And we think that the sliding of the ruler is a concern. Okay. So I would like to invite the reporter for the discussion. So firstly, I want to question about I observed that you use a water pipe to contain the ball when dropping the ball. So how do you make sure that the ball doesn't rotate in the how do you ensure that the ball didn't rotate in the pipe so that it won't change the experimental results?
So we use the pipe, the radius that is close to the ball, and we want to make sure the ball is in the almost a straight trajectory, and we try our best to make sure that it's straight.
But you make the ball's trajectory straight, but we don't see whether it has angular momentum.
Yeah, I think that because we have ensured the radius is not too big, the radius of the pipe is not too big. So we think that the area of the ankle will be slighted. Okay,
thank you. And I want to ask you about can you show again the data, the graphs you have plotted? Can you explain because you gloss over the data quite fast, and we don't understand the horizontal and vertical axes of your plots.
So which graph?
Can you elaborate on your graphs again, so that we can have a clear vision of what your experimental results? Yes, all these graphs. Can you explain how does your theory predicts this result, and can you elaborate on the deviations, starting from the first graph?
Okay, so for the first graph, it's about the width and the critical mass, and so that we believe that in our expectation, we think that the more the paper is the more width the paper is, the critical mass will increase. So this is the graph, and it kind of fit our expectation. And here's the width compared to the critical torque, and it's kind of like the last graph, so explain the same thing. And here's the width and the pressure loss of the torque. So we believe that the more the paper width is, the pressure will get in less, right? So the pressure loss torque will decrease.
Okay, so because the graph can't show, can you first explain what is the critical mass? Can you explain how do you define?
So the critical mass is the mass when the ruler falls off the table.
How do you define the ruler falling off the table? Is the sliding of the ruler, if the ruler sliding off the table is considered, or the ruler needs to be flipped over and dropped onto the ground?
Yeah, so we have observed this phenomenon. So we have observed that there are two conditions. First, it will slide off the table, and the second is that it will flip off the table by torque. So, but in this experiment, we want to define that the falling of the ruler is slide off the table.
But how does your torque model incorporate the sliding off situation? Because the points where the ruler contacts the table will be different if it is sliding off the table. So
Yeah.
how does your torque model predict this situation?
Yeah, so there will be a you mean like friction or something, right? For the
Yes, there
table.
will indeed. There will certainly be friction.
Yeah. So because what we want to measure is the critical mass. So we think that if the material remain the same, we want to we want to focus on the critical mass more instead of the falling.
You said you observed two cases of ruler falling off the table. One is sliding off, one is directly flipping over. But how does your results show these two conditions? Can you show me?
So since we define that slide off the table, so all these results, all this critical value is the value that when the ruler slide off the table.
So you mean so define critical mass, critical torque to be the points where the ruler will slide off the table. And do you mean that if the ruler flips off the table, the torque will definitely be larger? Do you think so?
Yeah, I believe.
Okay. And okay. Next, please. How do you define elasticity? If you mentioned you just compare them. How do you compare them?
So in the comparison, if the ruler will have a deviation, we will define it as a soft ruler. Like we use two materials. One is the wooden one, and one is the acrylic one.
So you apply constant force to the both of the ruler, and when it bends, you deem it as if it bends, then you deem it as elastic, and if it doesn't deform, you define it as inelastic. But that doesn't provide a quantitative analysis for the elasticity. I think you should improve on that. Maybe using the Hughes coefficient or using Young's modulus.
So I want to ask what material did you use for the elastic ruler?
I cannot provide my own experimental details.
Okay.
And for okay, so for modeling, we think that do you consider air pressure? You do take air pressure into considerations into your torque model. How did your theory incorporate air pressure? Can you show me?
So we use the integrating theories to calculate the air pressure within the ruler.
Okay, so mean that it so mean if so your theories is applicable to the inelastic ruler scenario, but how is your theory compatible with the elastic ruler? Or you didn't do the experiment with elastic ruler?
Sorry, can you clarify the question?
Is your theory compatible with elastic ruler?
Yeah, we believe that it can use the theory to use the.
But according to the basic assumptions of torque things, if you want your sorry, and do you observe that the ruler oscillates when you drop the ball, or do you think it's negligible?
Sorry, what do you mean by asking?
Because you mentioned that the volume under the paper and between the tables is an important parameter. But from your experiment, we see that the ball falls onto the ruler and the ruler will oscillate and thus lifting the paper. How do you take this phenomenon into consideration?
So you mean when the ruler is hit and it falls off the table?
No, I mean even if the ruler stays on the table, it will oscillate because the ball provides an impulse to the ruler and it will oscillate. This oscillation will cause the ruler to lift. How do you explain this phenomenon?
So we believe that it's a certain amount of air pressure went into the paper, but it's not. But like the mass is not big enough for the ruler to fall off. The torque is not big enough.
But your theory doesn't have any terms concerning the volume under the paper.
Yeah. So we didn't have a theory to explain how this phenomenon goes.
We believe that because the ruler lifts the paper up and causing the air to flow in, and thus losing the air pressure difference, so that the paper won't have a atmospheric pressure pressing down, so that the ruler will slide down. We think that you should elaborate more on the volume under the paper, so that we can investigate more clearly into the phenomenon. Okay, that's pretty much my question. So for the summary of the discussion, we asked about the details of the graph, and the reporter explained according to the graph. And as for the theory fit, the reporter thinks that the data points they do fit the theory they're citing, but we don't think the data points are enough for fitting. And the opponent did not define hard and soft well. We think that they should do a quantitative analysis on the rigidity of the ruler. And in theory, we should include a situation where the ruler just flips off, not just sliding down. Thank you.
Thank you to the opponent and the reporter's presentation. So I have some questions to the reporter on your experiment setup. So when you Do you change the mass of the ball that you draw on the ruler?
Yeah, we just think of the mass.
So that is what you define as critical mass.
So we define a critical mass as the ruler pull-up.
Okay. So you are varying the area of the paper each time.
The area.
Yes, you're changing the width. Okay, thank you. And this is a question for both the reporter and the opponent. Do you consider the contact time between the ball and the ruler?
Yeah, we did consider this, but we don't have the accurate enough barometer, so we didn't measure that.
The reporter did include the contact time into consideration because they use an angular impulse and the normal impulse. Okay.
Thank you. And can you open up your slides for your data graph? So looking at your graph, it didn't indicate where your data points are. I can't tell where exactly how many data points do you have.
So we have like 5 data because we have changed the width of we have changed 5 kinds of width.
Thank you. So can you add error bars to this graph?
So we did, but we didn't put it.
So you conducted this trial multiple times. Okay. And so this is a question for the reporter. How does your torque theory provide a qualitative relationship for your experiment? How does your theory give you a qualitative relationship? Can you provide an actual qualitative relationship to describe how you are extracting it?
So because of the lever theory, we can see that the counterclockwise torque is bigger.
I'm sorry, I meant can you find a quantitative relationship? I'm sorry, it's okay. Do you think, how do you think the reporter could create a quantitative relationship?
Quantitative.
As in, like, provide actual values to their theory. I'll be reviewing on topic 14 really quick. And this is the problem statement, and the reporter's main focus is on the effects of the atmospheric pressure on torque and the threshold value needing to hit off the ruler. So the report's presentation first opened on how they used their setup of using a water pipe, a ruler, brackets, and to set up the phenomenon. And then they described how they used the lever, the rule, the impulse momentum theory, torque, and integration theories in order to develop a model. And then they explained their experiments, the parameters they vary, which is with the width of the paper and other parameters such as the rigidity of the ruler, and they explained their prediction and results for them, and then presenting their conclusion. So the purpose of the reporter's presentation was that they were able to visually show the proof that air pressure is the main factor keeping the ruler on the table. They were able to create a good setup that can reduce the error of how the ball contacts with the ruler, and they were able to determine to confirm their predictions for the relationship between their parameters. However, there are some cons to the reporter, which is that they missed certain parameters such as the weight of the paper, and they ignored important, and they did not address certain calculations such as the transfer of momentum. And then and according to the problem statements, which required the reporter to look at the relationship with these parameters, the force outputs, the reporter never gave quantitative values for the force outputs, and causing them to never calculate any dimensions for the force output, and they also did not make errors in their data. And moving on to the components of performance, they explained the preliminary experiment and questioned their modeling and pushed some of the parameters. And the pros of the component was that they mentioned that they were able to point out some unclear definitions and point out the limits of the theory, but they did not directly analyze the opponent's data and did not completely understand some theories, such as the fact that the reporter were able to prove that air pressure was the cause of keeping the ruler on the table. In this the opponent asked the reporter about how did they determine the angle. The reporter were unclear on their response, and I would have added a scale to visually measure the angle. And the opponent asked the reporter to define hard and soft ruler, and the reporter tried to compare the rulers. While I would have suggested directly looking at the shape under the paper to try to quantify the ruler. And how to define the volume. The opponent asked the reporter about how they define the volume of the air under the paper. The reporter did not actually measure the dimensions of the volume, so I would have added a scale to directly measure the dimensions of the volume. And the opponent asked the reporter whether or not they defined the ruler as hard or as a rigid body, and they defined a hard ruler as yes and a soft ruler for no, and I agree with the reporter's statement. Some of the mispoints that the discussion missed was the exact transfer of momentum between the ball and the ruler, the lack of actual values for the impulse threshold by the ball, and they did not discuss the shape of the volume underneath the paper, and list some additional parameters such as the hanging length of the ruler, and they did not discuss any actual measurements of volume underneath the paper, and they also did not discuss torque and momentum of direction.
Reporter.
And second is the air volume under the paper. And third is they have mentioned we have consider they want to consider ruler as a rigid body or not. And fourth is we compare two kind of ruler to discuss the stiffness. And the fourth is that they want to define the slide and the folding of the ruler. And the fifth is that they think that the elastic should be considered. And for the reviewer, they have discussed about it. And for the reviewer, they have discussed about the ruler arrow bar and asked if they did the experiment multiple times or not. And so for the conclusion, we think that there's a lot of factors to be considered.
Okay, so now on to small question. Okay, so for the reporter, so can you go to your experimental thing? So can you give us some parameter that is most important in your experiment?
So in our experiment, we think that the air pressure is the most important parameter.
Okay, so for
I think that the elasticity of the ruler is the most, the elasticity and the ruler, how much the ruler lifts the paper is the most important parameter.
I think that the air pressure is the most important parameter, but it can be related to other parameters which the opponent has mentioned.
Okay, so let me ask a question for reporter. If you want to quantitatively predict, for example, critical mass, how will you improve your theory or your experiment setup?
So we think that we should consider more factors and make sure the factors will be accurate enough, and we should do multiple times of experiments to make sure the gap is not too big to.
Well, how do you predict? I mean, you predict. In your data, you just observe. At this critical mass, you will fall. Okay. But how do you predict?
So
Okay.
I would try to measure the velocity of the ball before colliding with the ruler and accounting for the hanging mass of the mass of the ball, and to try to calculate the impulse mass from the ruler.
We think that we should measure the elasticity of the ruler so that when the torque is applied, it will lift the paper up. And we need to quantify this, and then we can measure the air inside under the paper, so that the paper will slide off the table.
Well, my comment is okay. See, you all agree the air pressure is important, but you didn't measure the air pressure. How do you quantify? How do you qualitatively quantify your experiment data with your theory?
I would try adding a scale next to the setup to attempt to try to measure the volume of the paper and then relate the volume, the change in the volume to the pressure.
All right, so thank you. Okay.
supporter is 5, 5, 6, 5, 5. And for the opponent, 7, 9, 7, 6, 6. And for the reviewer, 6, 9, sorry, 7, 9, 6, 6, 6.
I give especially high score for opponent review, so I give a short comment. I think we almost have no problem because all questions almost already asked or comment by opponent and reviewer. So I think you do your work, your character very well. Yeah, that's good. And also have a short comment about the experiment. Because Professor Guan asked you that how to calculate the maximum critical condition. I think you can assume very simple condition to check the critical point. For example, you can assume the maximum pressure is one bar, okay, and no pressure under the program, because when that dipped, the pressure becomes very, very small. You can assume this condition, no deformation about the paper and so on. So you can get a very simple critical condition. That's the maximum condition. And then later you can assume, okay, if you can have a slower condition, you can have air leakage, and then you can assume some time, some critical time or some condition, then you have a lower critical condition. I think all of you can also do such kind of condition.
It shows especially for the report. You took a lot of time to experiment, and I want a lot of data points. And you did the experiment. You had plenty of time to expand it during your report, so don't waste your data.
Okay, so there's no more.
Maybe I make a last comment. Okay. If you want to make a prediction quantitatively, right? So several things you need to consider, right? So first, you need to have something to measure the pressure. Under the table, your pressure sensor or something, and then you need to have a theory to predict how when the ruler is tilted up, how much air is flowing in. Okay, how much? Okay, when you tilt up, how much volume of this tip will create, and how much air will flow in. So you need to have air flow in, and then you also have a vibration of how much air is created. And then you with this equation, then you need to solve what is the pressure inside your paper. Then you can do the quantitative prediction. Otherwise, you just hand waving, and also of course you can assume an ideal situation that would deviate from your experimental data. Okay, so quantitative theory needs to do those steps. Okay. Of course, it's very difficult for you because you it's only. But if you want to do the quantitative comparison between experiment and the theory, then you need to do that, and then you have pretty much good agreement between your experiment and your theory. Otherwise, now it's just qualitative theory. Okay. Right.
Okay, so let's end.